That was quite a lack. That's so cool. Kia ora everyone and welcome to NCA Level 3 Computer Science, Computer Graphics. Oh, I don't think we're doing that, are we, Tim? Oh, yeah, Computer Graphics, Computer
Computer
Vision.
vision
I
is
get it.
highlighted.
Sorry,
Yep.
aroha mai. It's the one that's highlighted. Oh,
I should probably.
welcome to the Computer Vision Computer Science session today with Tim. Tim, thank you so much for helping us out with this, and I'm really looking forward to doing some learning as well. Kia ora.
Okay. Oh, well, kia ora koutou. Thank you for joining us for this. Computer vision is, yeah, pretty cool topic in terms of it's just all around us. Students probably take it for granted these days. Just a few years ago, it was very science fiction-y and modern. It's just the idea of pointing computer cameras at things and having the computer recognize stuff that the camera's pointing at. So even something like Zoom can do that a wee bit, recognizes when there's faces there and that sort of thing. But we'll look at a whole lot of applications. I thought it'd be really good. So computer vision is not my area of expertise, but I've enjoyed sort of learning about it over the years alongside the NCA students. And so I'll share what I know about it. But maybe if people could just type into the chat roughly what your experience is with computer vision. Maybe you've taught it before, maybe you've not even thought about it before. Maybe you'll have some great ideas to contribute to. So I'll just let you type that into the chat, just a brief thing, so I know roughly where everyone's at. Here to learn, love that. Oh yeah. Yeah, yep, picking up speed signs. I mean, cars are a big application now, and even you know, not terribly flash cars sometimes have got cameras or well, they have got reversing cameras and all sorts of stuff, and often there's a bit of vision in there, let alone picking up warning signs and things. Cool. Oh, watch the video on the field guide. Excellent. That's David Thompson did that and gives a nice sort of overview of what we're going to be thinking about. Right. Okay. Well, I'll launch into it. So based on Tracy's comment, you can see the slides. And it's a level 3 standard, and it's the students have a choice of 3 topics for that. And it would be really cool if they have a very rough idea of why, what the choice is between the 3, just because computer science is not about any single one of these things and they all overlap. Computer vision has algorithms that have complexity. And actually, one way of thinking about computer vision is that it's just computer graphics in reverse, right? So computer graphics, we take some mathematical model of the real world with bodies and objects and things in it and produce a 2D image on the screen. Computer vision, you take a 2D image that's been taken by typically a camera and try and figure out what are all the objects in that, whether it's recognizing a face, and is it a particular person's face? Is it an object in front of the car that you're about to run into and it needs to slam the brakes on? Or is it an apple that's got some defect in it and will be sent to the local market instead of overseas? These are all current applications of vision. Right. So I've popped up a lot of the links that I'm using and the actual slides that I'm going to show you today. I'm going to put at this location here. Sorry, Tracy, I should have given that to you in advance. In fact, I can.
All good, Tim. I've just typed it in, so hopefully if someone could just test that I haven't transposed anything.
Actually, I've just remembered to paste it in myself. There you go. So,
awesome.
One of those will be correct. And I've got the full link there too, in case Bitly doesn't behave for you. Cool. So that's in the meeting chat. All right. So standard itself, 3 credits at level 3, which means, your students will commit about 30 hours of their life to it. Usual disclaimer, I'm going to try and cover it in less than 1 hour. So if it's not overwhelming, I haven't done my job. I'm going to throw you a fire hose of information, which hopefully you can go away and unpack, perhaps with the help of your students. The standard itself this year, as I mentioned, there's a choice of 3 topics and students just choose one of them. It says they're required to give short and or extended answers. I'm pretty sure that's and based on past exams to questions. And I think what will happen, we'll look in a minute. In fact, where is it? Yep, we'll look in a minute at exactly what's in there. But um, the um, the notes say that some specific topics that students will need to talk about, which some of them are very, well, not simple algorithms, but very particular ideas from computer vision. I would say that they would need to be able to explain those and probably, given an image or given a situation, talk about how that idea would apply. And then generally these exams, there's a later section which says pick a method or a technique that or an algorithm or something that you've looked into and talk about the social issues around it or the opportunities or whatever. So again, so that's one that students can prepare for quite a bit if they sort of dig deep into one particular technique or a couple of techniques, but have sort of figured out all the ideas and issues and opportunities and things around that. So that's what my takeaway from based on the past exams and the guidance that's been given. So yeah, computer vision, taking an image and figuring out what's in it. This is there's a video at the start of the field guide with David here, who is holding a good banana and a bad banana, and certainly that's a very strong application where they process millions of items of fruit every day and just choose which ones are good quality and which ones aren't and so on. But lots of other applications. So on the left, this is by no means exhaustive, but motion capture. A camera has got an image of someone running around in a scene with dots on them or holding some markers and figuring out where the person is and replacing that person with a dinosaur or a bear or whatever the character is meant to be in the movie or the image. Silly applications like just putting silly ears on people, recognizing where the face is and putting the ears on. Self-driving cars, big application, and that ranges from just simple things like figuring out where the lanes are, where the hazards are, and things like, as Bill pointed out, it's just spotting speed signs and so on. And then medical applications, and they are explicitly mentioned in the guide. So for this year in the specifications. So I would say you want your students to dig into some medical applications, which is not so much, well, sometimes it's cameras, monitoring patients, like looking at how they're walking after they're recovered from an injury, or even just checking whether they're wriggling around in bed and need some help, that sort of thing, through to MRIs and X-rays and other kinds of cameras that actually look inside the human body and figure out what's there. And also a big application, of course, is looking at samples of human tissue and so on to say, are these cancerous cells or are they not? And if you can classify those really quickly, or if you can get a computer to do all the hard work and highlight things that look a bit dodgy, then there's much better chance of detecting problems that need addressing. And of course, there's all the negatives that come with it. Privacy, knowing where people are because they've got walked in front of a camera, medical stuff, even, knowing that people have a particular illness or, something that may rear up in the future, and therefore doesn't necessarily make you feel good. Sometimes it's better not to know, but also maybe your insurance company will want to charge you more for life insurance or won't give you life insurance and that sort of thing. So there's lots of, as with any technology, the pluses and minuses. Despite all these many applications, there's a lot of basic ideas in there that are pretty much the same. And so from the specification, don't worry too much about this. I've just highlighted the key thing that it highlights four things. So one is basically image processing. You get a photograph and you have to, you need algorithms that will sort of clean it up and find edges in it and so on. We'll have a look at that pretty carefully. Obstacle detection. So how do you find things in the image? Feature extraction. And that's particularly for features are things like noses and eyes and ears in a picture of a human, or it might be cells in a medical image, or it might be limbs if in a sporting application where you're tracking someone doing sport or something like that. So it's the elements that you're looking for. And then medical diagnosis that I've just talked about. And we'll have the other words that are in here. I'll do my best to touch on them all as we go through. But the big picture, first of all, that hopefully your students have some foundation from previous years. Hopefully they're aware of how images are made out of pixels, and that pixels are generally in their raw form represented using red, green, blue RGB. If they haven't done that, there's quite a big section in the chapter in the field guide on data representation where they can throw their own image into it and zoom and see it. And of course, the other big picture is this whole thing about having this in NCA is just for students to sort of find out if they're interested in this sort of stuff, rather than being users of vision or users of graphics or users of AI. They actually have some understanding of how it works and how they might even do it themselves. So just to get back to the pixel kind of thing. So I've took a photo of a banana, and we've got this app in the field guide that you can zoom in and see the actual pixels. There it goes. So while that banana looked like a yellow thing on a slightly yellowish surface, really all the computer sees is a whole bunch of numbers. And the color yellow, actually, if you just look at the top left-hand corner here, that's not even yellow, is it? In fact, that's the shadow, isn't it? So if I look at the middle of a banana, and see the thing about computer vision, all it's got are these numbers. It can't see the colors. And so when red is high, if we look at the top left-hand corner, 212 red and 168 green and almost no blue, that mixture is the color yellow. So based on those numbers, we know we're looking at something yellow. Now, a lot of the algorithms in that we look at are going to be a lot simpler to work with if we work in black and white. And so there's an option here, which I have just eluding me now. Oh, here we go. Grayscale or RGB. So I'm changing it to grayscale. Because often computer vision will work separately with the red and the green and then the blue. And it's easier just to talk about the algorithms instead of in terms of grayscale. And the way that that's done is you just average the red, green, and blue values, and so that they're all the same, which means bright things have high numbers and dark things down here have low numbers. So 0 is black and 256 is white. So 106 means some sort of shade of gray in between. And then, so if we go back and look at the original image, I'm just zooming out again. Banana doesn't look so appetizing now, but that's what the computer can see. In fact, we can even tell it, here we showed the pixel background. If I turn that off, this is really what the computer sees, right? A whole lot of numbers. It's a digital image, it's a digital photo, it's a whole lot of digits. And so computer vision is about taking those numbers and figuring out what they really are. And that is sort of the simplified version of what it is. Now, to do vision, we think about human vision, and the sorry, I just saw the question, how essential to have the pixel RGB knowledge? Absolutely essential. It's pretty straightforward, right? A picture is just made out of a big block of pixels, typically a megapixel, a few megapixels, a few million pixels, and each of those pixels is represented using 3 numbers, because all of the algorithms for vision process those numbers. And so if they want to have any idea what those algorithms are doing, understanding the numbers just to the level that I just showed you is enough. Now, probably 10 minutes playing around with that app, and they can drop their own photos into it and just see what the colors are and what they mean. And there's some sliders in the field guide where they can play with RGB to figure out what they mean. That would be enough to give that essential knowledge.
Yeah, you sort of answered it after you started showing that image.
Right.
And I think it's to what depth, and you just sort of confirmed pretty much what you just showed us, or awareness of how that mechanism works, rather than what they used to learn. When was it, level 1 or that? Yeah. It used to be.
Yeah. It used to be quite a bit in that on level 1 on data representation. Yeah.
That's it. Yeah.
And they got into compression and other sorts of processing on those pixels, but no, that's about all there is to it.
Yeah.
And in some ways that takes a lot of the magic out of computer vision, right? Because humans, we do image processing. We can spot faces and cars and all sorts of things quite easily, but it's to break it down into all you've got is those numbers, and you have to do some processing on those numbers to figure out what the image is the challenge. So we're interested in obviously color. Objects have color, and faces and skin, and that has particular colors, and of course that raises some interesting issues too. You've probably heard about systems where the team forgot that not everyone has white skin and things like that. And then we're interested in shapes, whether typically the shape of a face or an object on the side of the road, or the shape of lungs, or whatever the thing is that you're looking for. Lighting is really significant. So most images have lots of shadows. If we go back to my yellow banana, actually, I think I've got a picture of it there. While we look at that and go, that's yellow, it's not really. It's got many colors, many shades of yellow on it. And in fact, some of it's quite dark, the bit that's in the shadow and that sort of thing. If you zoom in closely, there's probably not much difference between the dark part and the shadow of the banana and so on. And it's quite fun for kids to do that, and they realize that this really is kind of a tough problem. It's not as simple as just saying everything that's yellow is a banana and everything that's not yellow is not a banana. So lighting affects it. Often things are moving and you need to track things, and that adds, in particular, that raises the question of how fast the algorithms are, whether they can process in real time. So even an old digital camera used to be able to hold it up and it would put a yellow box around someone's face. That's a moderately, that's one of the algorithms that we'll look at how to do that. That's a fair bit of digital processing to do just to track people's faces moving around in a photo. And then we're looking for patterns of objects, and depth is another really big deal. How far into the image is something? So for that, we actually need to have, if we've got two cameras, just in the same way that humans have two eyes, then there's a few calculations we can use to calculate how far away an object is. And obviously, like if you're driving a car, that's really important. If there's an object on the road, but it's 200 meters away, you might react quite differently to it if it's 10 meters away. And also with organs inside the human body or anything like that, we're interested in where things are in the image. So a relatively simple thing to start with, but quite an important element of image processing is called edge detection. And it's in that photo. It's given a photo, draw a line around the edge of the objects that are in it. And so on the right-hand side, it's probably not quite the line that you would have drawn, and there's a whole lot of different processing that can go into that. In the notes, I've put in a live program. Here it is, that does edge detection. So this is, hopefully that's coming out all right. This is my camera being fed into an edge detector. And so in particular, if I hold up something with writing on, you can see that it's got half a chance of detecting what the writing is. And it's the first step towards finding objects in an image. And this particular one is quite good because you can adjust the threshold up here on the right. So if I create a really high threshold before it's prepared to detect anything, then things disappear. If I have a low threshold, then there's a lot of noise and rubbish in the background. And likewise at the top end, you can adjust that. And if the settings are wrong, then it's not what we would have considered an edge. So those settings have to be just right to get nice, clean images. And that in itself helps students to understand what some of the issues are. And you notice down here, it's running at about 60 frames per second. It's probably a wee bit hard to see it, but incredibly fast processing. So, as I move around and it's going through Zoom, goodness knows what it's looking like for you, but it's processing in real time, which is the ideal for image processing. But some image analysis is more difficult than that, and you can't process it and get back in real time, but that's all of matter. It's one of the trade-offs we have to make. Okay, so that's edge detection, and we've got a thing in the field guide where your students can experiment with edge detection. So the first thing is that any image will have noise in it. And in fact, that image, that pixel viewer image that I had here, let's just turn back on showing the background. Over here, this is a link from the vision chapter, which adds the ability to add noise to it. So if I just click on add noise, actually just, yeah. So I've clicked on add noise, and this is called salt and pepper noise, which is just random white and black dots added to the image. That's actually quite a bit. I might just knock that down to 3%. Right. So, and that just comes from cameras. If the light is a bit too low, it may literally be dust on the lens or something like that. But we acknowledge that a photograph is not absolutely sharp, color for color image of what's there. And so to remove noise, generally blurring is used. And there are several kinds of blurring your students can try out. Medium blurring is generally quite good. If I apply that, what it's done is it's blurred the noise. It's actually more or less got rid of it. And whereas if we can try Gaussian blurring, with that one, you can see it's actually blurred the image as well, but it has blurred out some of the noise. And so when you're trying to detect an edge, you don't want that noise to come through as being random edges in the picture, right? So because they're now blurred, they aren't a sharp edge, whereas the edge of the banana still is a sharp edge. So that's the first step. The other thing that I might just bring in here is that it's got the idea of a convolutional kernel, which is a really big word for a relatively simple idea. It's a list of numbers, and all that it does is for a particular pixel, all of the surrounding pixels get multiplied by this number and added together. Now, in this case, it starts off with all ones, and so the middle one here, that is the pixel that's being blurred. So this happens to every single pixel, as it says, take one of that pixel and one of the pixel above and one of the pixel below. So actually we can zoom in and look at this. So for example, there's a pixel here in the middle, it's 79, but it says we'll add the one above, 73 and 79 and 85. And in fact, it's the two above and the two below and the two to the left and the two to the right. Add all of those up and work out the average and replace that pixel with the average of all of those 25 pixels. Okay. And that's and that is exactly what happened here. And it makes the image more blurred, which in general is not what you want to do to images. You want them to be nice and sharp, but it means that it gets rid of noise that might come across as the edge of something in it. Now, part of the reason I want to introduce this is the idea of a convolutional kernel, big word, comes up over and over in image processing, where we multiply all of the surrounding pixels by a particular value. And in this one, your students can actually try things out. So I could say, well, I'm going to multiply the pixel in question by 4, and then say the pixels that are close to it, like the ones that are just one away, I'm going to multiply all of those by 2. So they're worth twice as much. And then the ones that are further away are multiplied by 1. So it gives more weight to the actual pixel itself, but it brings in a little bit of the color from the surrounding pixels. Right? So it's just mixing together those values. Pretty simple multiplication. Just a heads up, for those of you who have worked with matrix multiplication, it is not matrix multiplication. Okay, convolution just means multiply all the surrounding stuff by those values. If you haven't done matrix multiplication, fine. But if I apply that blur, that's how that comes out. We could do a blur where everything is 0. No, I'm having too much fun. Except the pixel itself. Whoops. I'll make 1. And of course, that just changes it to the original image, right? It says take one of the pixel and nothing of the surrounding pixels, apply that blur, and we've got the original image. Okay, so students can play around with that and play around with different ways of blurring an image. Really important step. Oh, which app am I using? Oh, let me just, I'll put the link in here. So this is in the field guide. Oops. And if you go through the computer vision section of the field guide, it actually has a section on blurring, and this is linked from that section on blurring. But yeah, you can go straight to it yourself. It starts with an image that's probably not ideal for this, but you just drop a photo on top of it, your own photo, and then you can start playing around with your photo. Yeah. There's another version of this interactive, we call it, without all the convolution kernels that enables students just to explore pictures more easily. But this one's in the vision one. All right. So we've removed noise, and that's a whole lifetime of research on its own for some people. Now, once we've got a clean image, we've just got a bunch of numbers, and there's actually an unplugged activity from University of Colorado, actually, University of Mines in Colorado. I'll put the link in our notes to that one. And this is one we do with primary school students. We just give them these numbers, and we say, look, these numbers are the brightness of every pixel. Where are the edges in the pixel? Excuse me. Might let you have a look at it. What are two numbers where you think there's an edge in the image? Just pop your mic on or type it in. Excuse me. Right, so from 21 to 103. Yeah. In fact, there you go. I happen to have that one lined up. So the brightness is 21, 21, 21. So it's not very bright. Then suddenly 103, quite bright. And then, so that's probably the edge of an image. And in fact, students can just go through, print these out, and you just get them with a pen to go through and look for where there's sudden changes. And there's a horizontal change, right? And so we're looking for vertical changes as well as horizontal changes. And by tracking through those sudden changes, we start to figure out what the shape is. And there's about 3 of these worksheets available on the website that have different pictures in it that students can try and figure out. Now, the person who came up with this idea was a guy called Kenny, and so it's called Kenny Edge Detection, and you can actually do it in a spreadsheet. So here I've done it in a spreadsheet. I just put in a whole lot of pixel values, and then in some cells over here, I just worked out the difference. So 197 minus 90 is 7. 191 minus 97 is -6. 193 minus 191 is 2, and so on. And that is a convolutional kernel. In fact, the kernel is 1 minus 1, which means take a particular value and add -1 of the pixel to the right of it. Okay, which is just subtracting 2 adjacent pixels. Actually, strictly what I did was -1, 1, but that convolutional kernel, if you pass it over the whole image, will just simply produce those differences, right? And then on the right-hand side, I just put an if statement in the spreadsheet that said if the number is bigger than 10 or less than -10, then put an asterisk. And now that asterisk is the edge. It's the Kenny edge detection, right? I've detected where the edges are in that particular picture, and students could play around with that and try out different edges. And so what happens if something's gradually changing, 23, 25, 27, 24, 25, 27, which is not unusual, that's not an edge. It doesn't differ by 10. But then if it suddenly jumps up to 36 or something, that counts as an edge. And then the students, of course, can start to think about, well, what is the threshold? Does a jump of 10 count as an edge? Should it be 20, and so on? And in practice, these things adapt depending on the contrast of the image and things like that. But gives them a really good idea of what the real issues are. And it's a very simple convolutional kernel that basically means take a particular pixel and subtract -1 of the one next to it, and that's the difference between 2 pixels. That's a really fancy way of saying subtract 2 values. Oh, Ruth's asking if it's a star. Well, you will have to complete it and hand it in after class to be sure. Cool. But actually, yes, it is. But I think it's a nice way for students to experience computer vision firsthand. Now, so the simple canny filter of just subtracting two adjacent pixels, and canny has come to mean all sorts of convolutional kernels applied to try and find differences, but the simple one there is a bit crude, and it won't always detect edges, and sometimes it finds edges where there aren't edges and things like that. And so another one that's quite common is called the Sobel filter, which is mentioned in the standard as something that might come up this year. And the Sobel filter uses a bigger convolutional kernel, 3 by 3, and it so it's less sensitive to noise, and it finds boundaries. And of course, your students can experiment using a Sobel filter and a canny filter. There's quite a few online sites too where you can put these things in and have them process images and so on. But just to look at this one here, you remember when we were looking at the star, I was looking along horizontally for differences, but then sometimes we looked vertically for differences as well. And the Sobel filter, this GX is the horizontal, it's looking for horizontal differences. GY is looking for vertical differences. And using those two values, it can combine them using Pythagoras, if you really want to know, to work out where the edge is and what the angle of that edge is. Okay, which also becomes interesting if you're trying to work out what an object is, and that maybe it's got a curved edge and things like that. Now, hopefully the convolutional filter, I mean, it just works the same as the other ones. So this, in the GX, the middle pixel actually has zero impact on what the slope is. The pixel to the left of it is multiplied by -2, and the pixel to the right is multiplied by +2. In other words, it subtracts the left-hand pixel from the right-hand pixel and gives it double weight. It also looks at the line above of pixels and subtracts the left-hand one from the right-hand one, but only with a single weight. So it's basically saying I'm most interested in the row that my pixel is in. Doesn't matter what my pixel value is if the one to the right is if there's a sudden change between the one to the left and the one to the right, then this is probably an edge. Okay, so that'll give you quite a big number. And then the vertical one is the same, except it's going vertically. It's saying, look at the pixel above my current pixel, give it a weight of -2, the one below +2. So is there a big difference in value between the pixel above and the pixel below? If it all looks rather mathematical, just plonk in some values. If the one above is 50 and the one below is 50, then 50 times -2 is -100. 50 times +2 is +100. Add them together, it's 0. So there's 0 change there. On the other hand, if this one was 20 and that one is 40, then -2 times 20, that's -40, plus 2 times 40 is 80. So it's 80 minus 40. That gives a difference of 40. That's a big number, and therefore there's probably an edge if we're going from 20 to 40. Okay. Again, if students play around with some numbers, they start to see how these are working. And again, just going back to this example that I had. Here it is. So what you're seeing here, with my face and hands and everything being detected, it's literally those calculations being done 60 times a second on about 1 million pixels on the screen. So 60 million times a second, those very simple calculations are being done over and over, and the net effect is it's showing some of the objects in the image. Okay. Any questions at this stage? Does that look achievable for? By the way, here's Wikipedia's got a good thing about kernels as well, how they work. A few examples, like this kernel here with 1 and the 0 just gives you the original image and so on. Right. Yeah. Any questions, concerns? Is that doable? It's pretty simple arithmetic. It's just adding and subtracting and multiplying numbers. But it's a digital system and it processes digits. So that's exactly what it has to do. Now, I'll just take a quick aside now and say these are very fast methods because they're so simple. Also, you may have heard of GPUs, graphical processing unit, that most computers these days often come with a GPU as well as a CPU. GPUs are very good at these multiplications. You would just say, look, here's 1,000,000 pixels, and here's 9 numbers. Please multiply and add those 9 numbers over the 1,000,000 pixels. And a GPU goes, that's exactly what I'm wired up for. Whereas a CPU would need to have a loop that goes through every pixel and process them one at a time. A GPU just whacks it through and very quickly in one go. GPUs were originally made for creating graphics, but it turns out they're very good for computer vision. It also turns out that they're good for Bitcoin mining and a whole bunch of other things, and very good for large language models for AI. So NVIDIA in particular, who produced GPUs, they thought the gaming market was going to be it. Their stocks have just gone through the roof because GPUs are needed for all these different things. Right. Just here's a Sobel filter, just to give you an idea. So if the original image is a white square in the middle of a black page, the X gradient going along, it's suddenly there's an increase. So there's a big high number here, and then no change all through that, and then a sudden decrease. The Y gradient, it spots the increase and the decrease vertically. And then if you just take the magnitude or the absolute value, so -40, we just say, well, that's 40, difference of 40. Then we've ended up with an outline of what the image was, a square in the middle of an object. And even if it was a black square on a white background, we'd still come out with the same edge detection. All it's looking for is sudden changes. So it's something your students can get their teeth into, and very practical applications. Okay, next application, computer vision using for facial recognition. This is a bit more complicated, and I should say for a lot of applications now, we're going to look at some fairly fast, simple techniques, because as with a lot of things in teaching students, it's a lot easier to use traditional ways of doing it or simplified ways of doing it so they get the idea. A lot of this stuff now is being replaced by AI, where with deep learning and neural nets, and I'll talk about that in a wee while. But the thing about that is you can't really unpick what's going on. AI can't generally explain to you why it made a particular choice. It might say these cells look cancerous, but if you say why, it doesn't. I don't know. It's just the model that I've formed says that these are the same kind of pattern as other cancerous cells that you've shown me in the past. Whereas the more traditional techniques can actually say, oh, it's because there's a transition in color from here to here, or there's a lot of green in it, or whatever it is that it uses. So the value of looking at the older techniques is that students understand what's behind the scenes. They are very fast techniques and are still used when speed is important. But some of the AI-based techniques will also come into it, which we'll look at in a minute. So facial recognition, there's a few key things that go on. So the first thing is when you get an image of a face, and by the way, those 4 pictures are all the same person. How do you know that? I mean, so the photo system I was using recognized them all as the same person. And so to compare 2 different faces, first of all, you need to rotate it. So if I'm looking this way, then it needs to do a mathematical operation to get what my features are like sort of head on, so that it can compare it with other faces at the same angle and the same size. And then there's often a mathematical model, and particularly we've talked already about features, and AI works with features as well. So we're looking for things like eyes and ears and the shape of the outline of the face, which is just edge detection, and the width of the mouth, the position of the nose, and where they all are relative to each other. So all 4 of these images, the relative distances between the mouth, the nose, the ears, the eyes, all those sort of things match up. And there are many, many other features that are used in there as well to try and verify that it's the same face. Another option is just template matching, where you have 2 photos, they've both got pixels in it, and you just say, do the pixels in this photo match the pixels in that photo? It's pretty crude, pretty simple, very fast, but it only really works if you've got very uniform objects. Like maybe you've got a manufacturing line that's producing some particular, like a pen or something like that. And so every pen should be absolutely identical. and it's fine to match a picture of this pen with a picture of the next pen that comes out. And if there's a fault in the way that it came out, the images won't match exactly. Right. Another method, people make 3D models, and that's quite important for security. So probably when you've scanned your face to open your phone or something like that, you probably had to scan it from different angles, and the system's making a three-dimensional model of your face so that when you look at it from a different angle, it can work out what the 2D image would be from that particular angle. Also with faces, and particularly with things like photo collections, there's things like metadata, which is the time and the location of the photo. If two people are in the same photo or have photos taken at the same time, then it's obviously not the same people. So you might have people who are brothers that almost look the same, but if they're in the same photo, it's probably not the same person, and so on. So there's a whole lot of other things that can be used. So the method that's called out in the standard, particularly, is the Viola-Jones. Dr. Viola and Dr. Jones did this. And again, we've actually got an interactive in the field guide. Here it is. You can drop your own photo of a human face in here. But what it does, it's sort of a game for students to play. We talk about ha features or ha-like features. And up here in the corner, you'll see dragging around this image, which has got a white and a black block in it. And this is a convolutional kernel, right? It's just a bunch of, so high numbers and low numbers. But if I place them on the edge of this person's face, there we go. The edge of their image, you'll see over here that counts as being found. I've found 1 out of 5 features, because if you run that convolution over that image, then it matches quite nicely. You've got the light background and the dark here, and that'll give a high number. This one here, it's got a square in the middle. That might find something like an eye. Apologies to the people who are having their faces messed up with these. But there we go. I found another match there. So it says, look, there's some object here that is, dark in the middle and light on the outside. If I put it over here, yep, that also counts as an eye. If I put it on her forehead, it doesn't match, and because there's not an eye in the middle of her forehead. And so effectively what Viola-Jones algorithm does is it runs this pattern over the whole image from top to bottom, left to right, and then wherever there's a match, it says, okay, that matches that particular shape. Maybe it's the edge of a face, maybe it's an eye, or something like that. And of course, if you find 2 eyes and they're surrounded by, the edge of a face, sorry, if there are 2 dots surrounded by the edge of a face, then that's probably an eye, okay, or 2 eyes and so on. So that's how the Viola-Jones algorithm works, and your students can try it out. It's also got a Find Faces button here that actually runs the algorithm over it and tries to find those features. Notice it's a bit crude. The guy with the glasses, it didn't quite find his face that well. But they can drop in their own photos and just see if they can fool it. Put in a face with 3 eyes or something if they want, and see what it thinks of that. Okay. So it does use machine learning, and which is a simpler form of AI, which basically is statistics. It's saying, most of the time we see this pattern, it turns out to be an eye or a face and so on. So it can be, machine learning is about training. You show it lots of faces and train it on those faces. Which also brings up, recognizing faces, it needs training. It can't just look at someone and say who they are. It needs to be shown some images of that person, work out what the features are for that particular individual, and then learn from that. Now, a lot of contemporary systems also use neural networks, convolutional neural networks. I mean, you see that convolution is quite important, or CNNs, which basically are very hard to figure out what's going inside them. But there's a diagram here from Wikipedia actually, but you have some sort of input, and these could be a whole lot of pixel values or something like that, and you have an output, and when you're training it, you set that output to the value that you want, and then in between you have these uh, neurons. They're not human neurons, but they're just simple mathematical equations that says, if I get this value and that value, I'll multiply it by some number and add it to a couple of numbers, and put it into the next value. That's the convolution that's happening. So it's as simple as what we were doing earlier with multiplying and adding pixels. But it tries to figure out what numbers to multiply by and what numbers to add by and so on. And that gets stored away as a neuron. Okay. Again, it's an approximation to a human neuron, but it kind of works. And these neural networks, the numbers inside them start picking up the patterns that when you train it on a particular input and say you should produce this output, you can then give it a different input, like a different photo of the same person. And if it's trained well, then the output will say, oh, it's that person. It matches the image that I've seen before. It's a bit deeper for students to get into, but in the end, CNNs do come up quite a bit in terms of how image recognition works. So each layer in it reduces the maps of the features, and features might be bright spots, dark spots, eyes, hair, more pattern matches, that sort of stuff. And then it does some sort of classification. The simple one is it a face or not a face, which is just putting a box around the faces in the picture, which is a common application, or it actually matches it with a particular identity. It's been trained on that person's face and tries to match the identity. But it needs really large data sets to train, takes a lot of time, a lot of training. If you think being a teacher is tough, you try teaching one of these things, except, of course, you can throw billions of items of data at it and it'll just train in a matter of minutes or days or whatever, depending on how much data you've got. And so one moderately common method that is based on this is called YOLO, which I think stands for you only look once. It doesn't really come up it's getting a bit beyond what the standard expects, but this you can sort of see that the basic stuff that we were looking at helps students to understand some of the more sophisticated methods. And again, remember, the basic stuff works very fast and it's a little crude, but it works quickly. Definitely has applications. The stuff that uses neural networks, a lot slower, a lot more demanding in processing power, but can be more accurate. Right. Another application I just thought I mentioned in passing is text recognition, that you can point an app at some text, it recognizes the shapes. And you can see, again, edge detection would be really important there, detect the edges of the shapes, map those shapes onto a dictionary of what the shapes are in that language, look them up. So that's a more straightforward kind of application. Now, depth is really important. Humans have good depth perception, and we perceive it's quite good for your students to look into how they perceive depth. One of the key reasons we can perceive depth is we have two eyes, binocular vision, and so it's often robots and so on use two cameras, not just to make them look more human-like, but because if you're looking at something from two angles, you can figure out what the depth is. That's not the only way. Two other ways that we do. In fact, one of my students only has one eye, but he still has depth perception much of the time. And one of the things is occlusion, right? So, which of my hands is closer to the camera? Well, obviously the one that you can see is closer, and the one you can't see is further away, because it's occluded, it's hidden. And the other one is is parallax, that basically as things get closer, they're larger, and as they get further away, they get smaller. So if you know how big the object is meant to be, you can figure out how far away it is. Of course, that's how people can do optical illusions. You put a really small object close to the camera and it looks big, and vice versa. So binocular vision is one way of doing 3D depth detection. And this is one that your students can dig into. It gives them something to talk about again. And, remember that the exam for vision would say, talk about a technique and explain how it works and what the pros and cons are and all that sort of stuff. And we've got an activity in the field guide for this where they don't need a binocular camera. They just use one camera and take two photos, one photo here and one photo here, and just measure how far apart the two photos are. So they've sort of simulated a binocular camera, And then once they've got the two photos, the way binocular vision works in image processing is that you need to find the same object in the two images. So as humans, we could easily mark, the center of that orange and the center of the orange there. They're not in the same location in those photos because, of course, the camera's moved in those two photos. And then there's a formula. It's not too hard, but basically, if you know the distance between the cameras, the number of pixels wide that the image is, the angle of the view, and that angle is dictated by your camera. You can measure it. Any particular camera, you get a wide angle camera or a narrow angle camera or whatever, but you can work out the angle of view that your camera has, and the coordinates of the object in your two images. So, where that orange is, maybe it's 20 pixels from the left in one image and 26 pixels from the left in the other image. Those two numbers there, there's a relatively straightforward formula that you pop that into, just based on those measurements. And that's how binocular cameras work. So your kids can actually work that out. And then the idea is that they measure the depth of the object and see if they've worked it out correctly, see if the formula works. And what they'll find is it's not perfectly accurate because, of course, all those things are hard to measure absolutely accurately. And it's only accurate down to the pixel. But it means they've actually worked through the calculations for binocular vision, and get an idea exactly what's going on with those cameras on a robot that have got two eyes. The other way that depth is measured, a common way, is LiDAR, which you might have come across. So, self-driving cars famously have a LiDAR unit on the top that's scanning. So that this blue box here is the LiDAR, and it's sending out a rotating laser beam. So it's one laser beam that's gradually rotating around, and it hits objects and bounces back. And it literally measures how long it takes the laser to go to an object, hit it, and bounce back. And that laser is traveling at the speed of light. And if you know how fast something is and you time how long it takes to bounce back, then you know how far it's traveled. So, the distance to an object is just the speed of light times however long the laser took to bounce back, divided by 2, because of course it went out to the object and back. And so you only want half that distance of travel. So that's how a LiDAR works. It's amazing that it works at all, really. It's pretty remarkable. And but also, as this illustration shows, we've got a round object there, but if you're sitting here, all it really sees is the near edge of that object. It can't see through objects or anything like that. And so as a human, we would see the shading around a circular object or something, and it would make us think, oh, that's probably circular. Here, the depth tells us that it's circular. But we don't know what's behind it. We don't know if it's a full circle or whatever. It doesn't really matter if you're driving a car. You just don't want to collide with it. But these are all problems with vision that become quite acute. If nothing else, working on this, I think, will give your students an appreciation of how amazing human vision is. I said I'd talk about medical applications. So just think about X-rays, MRIs, CT scans. These are all like the LiDAR, right? They send out emissions and measure what happens. With the X-ray, how much of it gets through. With the MRI, it's actually resonating things inside the objects. And so you've got some really interesting three-dimensional equations to do to try and put together what's inside. If you're taking a photo of a heart or something like that, you're trying to work out if someone's got a problem with their heart, you can do a 3D reconstruction. So that's a really complicated form of computer vision. Cancer detection, looking at cells that have been biopsied, and looking for patterns in the cells that show cancer. Retinal images, if you've ever had your eyes scanned, these days they take a photograph of your eye and tell you if it's, you're getting a bit dodgy in the eyes. And those images get, again, it's funny, isn't it? Computer vision of the human eye, trying to work out if there's anything wrong inside it. Patient monitoring, I mentioned, like you might just have a camera on a room to spot if a patient is in pain or if they're moving or something like that. Or again, for physiotherapy, if someone's learning to walk again after an accident, to track their walking and to, maybe give them some feedback. Of course, that's also used in sports a lot too. Like, a rowing team might have a looking at their rowing patterns and tell them, oh no, you're just lifting it a little bit too high here, or your legs not quite in the right place or something. And then infection control, which ranges from just tracking where people are, during COVID, and that there was a lot of interest in who had crossed paths and so on. I don't think we were quite up for the privacy of tracking everyone everywhere with cameras. But in a hospital or in a very sensitive location or something, it may be really useful to know which people have been near each other and so on, for that purpose. So a lot more applications and that's just, there are way more than that as well. But lots that your students could look into and think about how they work, but that rely on computer vision. You will need to keep them focused on computer vision because it's other things not involving vision that do this as well. And I mentioned before, one of the downsides of some of the machine learning AI systems is that they don't explain why they made a decision. So there's a lot of interest in decision trees, particularly in medicine, which can explain the decisions. And so, I mean, this is a decision tree here. It just simply, decision trees get used in lots of applications. You start at the top of the tree and you might ask someone, what's your age? If it's more than 54, you go down the left-hand branch. Okay, what's your sex? If they say female, then again, you look at the age, and if it's less than or equal to 63, and what kind of chest pain. And in fact, sometimes I think when you go to the doctor, they are basically working with a decision tree, right? They're just saying, have you ever done this? Oh, no, yes, you have. Okay, in that case, was it, more than this or more than that? And what's your blood measurements and so on. And at the bottom of the tree, there's a decision based on all of those questions. And it may be that in some cases you wouldn't even go down the branch of tree like, because you already know the answer. So that's an explanation. So where computer vision is saying, I think this person has this disease. And if it was a CNN, then it can't really tell you why. But if it produces a decision tree, then it can. And so there's a lot of interest in explainable AI or explainable CV, explainable computer vision that explains why it made a decision. Otherwise, it may be making the decision for the wrong reason. One of the examples of computer vision is you could take a whole lot of photos of horses and a whole lot of photos of cats and train it the difference between a horse and a cat. But it might turn out that all you've really trained it is a horse is something in a green field and a cat is something inside a house. And it's not actually detecting the shape of the cat. It's just detecting whether it's got green in the background or whether it's got a house in the background. And that's probably a pretty reliable way of saying if something is a cat or a horse. But it would have been nice to have known the decision tree behind it so that you'd go, oh, okay, it does work, but it's not using the right features for making that decision. And it'll be the same with medical things. It might just say, oh, if you're male, then you're probably going to get this disease. That might be true, but you don't really want that to be the basis of saying that someone's got a particular disease. And then so a random forest is just a whole lot of decision trees. So there's a technique where basically lots of decision trees are made and they're combined. So forest is the technical term for lots of trees in computer science, and they get combined to try and make a sensible decision. One thing I thought I should mention is that all of that so far doesn't really involve any computer programming. It just involves looking at images and ideas. You can do, there's a system called OpenCV, Open Computer Vision, that is free. You can load it into Python. It's a library and just do computer vision in it. It's not required for the standard at all. But if you've got students who are into programming, like here is the program you need to take a picture and put rectangles around the faces in that picture. Okay, so it's pretty straight. It does a lot for you. You don't always see what's going on behind, but all it's done is it's passed it to a classifier using, you can see the HAR cascades or the HAR convolutional kernels, right? So it's using those, and which it's loaded from a file, and loads that into a list, and then for everything in the list, it draws a rectangle around those things in that list. So that's actually about a 5-line program that basically draws squares around faces and tracks where they are. So some of your students might find that interesting to look at. It forces them to think about things like where are the pixels how bright is bright. You notice the number 255 there. When you've worked on data representation, 255 is a nice round number. It's the biggest 8-bit number. 0 is, so 255 generally means white, 0 generally means black, and so on. So it forces them to work with those things, but not at all a requirement, but it is a way they can get into it. And by the way, large language models are quite good at generating OpenCV code, so that it's not that they have to learn a whole lot of things to be able to use it. I put this in bright green so I wouldn't forget it. The EndNote for the standard says that they need insightful conclusions, so things like innovative and imaginative connections and so on. For excellence, this is for excellence, so you want your students to have had the opportunity to think about those things. And so here are just some of the wider issues. I've mentioned most of them so far anyway, I think. But, issues like what privacy does this potentially hurt and also help? How does it help safety? Is it good for detecting crime? Is it good for detecting faults in equipment? Like, maybe there's a wheel that's about to come off a vehicle or something, a component that's about to come out of a machine and hurt someone or whatever. Or just, this fruit looks diseased, this fruit looks like it's really good, that sort of thing. Self-driving cars, and then the issues around, who's responsible if the self-driving car causes an accident. Do we need new infrastructure? Like if the computer vision is detecting road signs and patterns on the road, should we put better patterns on the road? Should we have particular road signs that are easy to read and things like that? They were all designed for humans to read them. And then sort of other general issues I've talked about, some methods are fast enough that they'll process in real time. If you're driving a car, you want it to find hazards in real time before you hit them, or, so it can automatically steer around them and that sort of thing. But if you want really accurate, like if you're doing a scan of someone's heart to try and figure out what disease their heart has, you don't mind if it spends 10 minutes processing that image to get a really, really clear image of their heart. So that you can look at it really carefully. And so, different contexts require different demands. The fact that we're using GPUs for a lot of this processing, that uses a lot of energy, a lot of power. And so, again, sometimes it's a case of the rich benefit and those that can't afford expensive computing are stuck without all these things as well. So that's just sort of touching on the surface of some of the issues that can come up too when we think about computer vision. Get your students thinking beyond just pixels and convolutional kernels. Whoa, okay. There's a little bit about computer vision. Sort of used up the time, but I guess, Tracy, maybe there's the odd question, or we can close off and chat a wee bit afterwards.
Absolutely. And Tim, thank you. Every time we do these sessions, I learn so much more, and I'm really grateful that we get to just to have this opportunity to learn more about computer vision and how it all works. And it's literally right under our noses all the time, isn't it? So that's really cool. I'm just going to find our code here to close.
Can I ask a question?
Yeah, go for it.
Oh, it was just about the convolutional neural network, which seems quite complicated, yet they're expected to ask questions about it. So do you have any idea, Tim, about what we could expect, or how much sort of insight they should have into that as a technique?
I mean, I don't know. But my best guess is that these standards have never required masses of mathematics or that sort of thing. It's sort of understanding the point of them and the general idea of how they work. There are really good websites that illustrate sort of the general idea, and students can train a CNN and sort of get an idea about what's going on and so on. And so I think if I was preparing a student, I'd want them to be able to talk about them without making stuff up, like having a rough idea about how they work, the language around them. So there's training, there's supervised learning, which is what teachers do. You tell them what the output should be and for a particular input, and then testing to see if it does do that and so I think those are the kind of concepts that are in there. And there are websites where they can train those sort of things. Actually,
Okay.
I'll try and pop one in the notes, because it's when you start training things that you start realizing that you need a lot of training data. There's things where you can just literally put up photos, or actually there's one on Google AI have got one on poses where you could do like paper, scissors, rock, and it's literally your camera is you just train it with lots of rock pictures and lots of paper pictures from your camera, and then show it a picture, and you can start to see, like, as you unfold your hand, it goes, oh, this is 90% rock, but 20%, 10% paper, and it's all, and but it's only based on how you've trained it in there. And I think those, when they've had that sort of experience, they can say, when I trained the neural network, I realized that, there sometimes it's uncertain and that these things can happen, and I had to do a lot of inputs and so on. To me, that seems to be the kind of level that would be reasonable. Yeah.
Thanks.
Very cool. Tim, I'm going to ask the Google Draw app that we're using in junior and senior primary, primary, where they've got like billions of people drawing different things and it's guessing. Is that also computer vision, or is that using something else?
Yeah, it is a very simple form of computer vision. It's probably getting a wee bit away from hardcore computer vision, because you're talking about black and white outline drawings. So the edge detection is done for it. It knows where you've drawn before it tries to recognize the thing. But Google do have, see if I can find it quickly. I'll pop it into the notes anyway.
Cool.
But it's designed for kids, and you can basically choose what you want to train. Like it's got an example of a kid doing sort of guitar versus piano or something like that, and trying to train it, when the image is you playing a guitar and when it's you playing a piano, whatever it is. Yeah, so but that is vision, because it's literally a 2D picture of you being processed to try and figure out something about what's in that image. Yeah.
Makes sense.
I mean, this,
That's cool.
most of what we've talked about, the basic idea of computer vision is you've got some sort of photograph or video from a webcam typically, and you're trying to figure out what's in it and where things are in it or who it is. Yeah.
And I guess the question around the maths, would it be fair to say they need to understand how the algorithm works, not necessarily be able to calculate it?
Yeah. And that's right. I mean, like with like the Sobel filter, it's basically saying it's it's looking at the surrounding pixels and looking for big differences in the surrounding pixels. That's the point of it. If they do the maths by hand, they'll start to see, oh, it's that simple. It's just this value minus that value. And if the difference is really big, of course I get a big value out of it and so on. That's all there is to it. Um, but it means when they're talking about those sort of things, they're doing it rather than just there's a mathy thing that happens and next minute, you've got an edge marked. Yeah. Might give an algorithm some numbers. Yeah, could do. I mean, yeah, in which case, if your students know how to use a convolutional kernel, then that's, which it's just not hard, right? It's just multiply each number and add them together. Um, yeah. Yeah, you're right. Yeah, the Bresnam algorithm required a little bit of calculation as well. Are they allowed calculators with them? Yeah, I'm not sure. I mean, most of these are calculations that probably most adults wouldn't hesitate to do, 40 plus 60 minus 20. But I know some of your students might freak out if they have to do a calculation like that. Yeah.
Very cool.
Hmm.
We're more than happy to stay on
I'll
that.
just
Sorry,
qualify it
Tim.
by saying I don't think it's a test of arithmetic. If you can't
Mm.
work out 43 times 7 minus 26, then well, if you get failed for that, then it's testing the wrong thing. Yeah. Yeah, a simple calculator that makes sense because it's not a test of arithmetic, it's a test of maths, not arithmetic. Yeah.
Very good.
Cool.
If everyone's okay, I'll say
Yeah.
karakia
Thanks,
to end so that everyone can go off to their busy evenings. So thank you very much, Tim. Ngā mihi nui ki a koe. It's been amazing again. And we'll stay on for questions afterwards as well. Whakataka te hau ki te uru, whakataka te hau ki te tonga, kia mā kina kina kiuta, ka mā taratara ki tai, e he ake ana te atakura, he tio, he hoka, he hauhu, te hei mauri ora. Kia ora everyone, and everyone who's watching online, I'm just going to close the recording now.